So, in today's most wonderful edition of ENGR 315A, we're going to be kind of wrapping up our discussion of bending with a statically indeterminate beam, as shown. Isn't it pretty in all of its PowerPoint art glory? So we'll be working our way through this problem today, seeing what we can do with it. And as Nick just asked, on Wednesday, we're going to be going through a review for the test next Wednesday. If you have questions, please bring them to the review on Wednesday. If we need more time, we can make more time, especially if you let me know what your questions are beforehand. We can try to set up as much time as we need. But that's only if you let me know beforehand what questions you have. All right. I also just don't know how much time needs budgeted. In terms of other news, I think that is all.
What is?
Oh yeah, and I'll have homework 7 back to you today or tomorrow. Sorry, what's up?
What's the first topic that's covered on the test?
The topic covered on the test are, hang on to that thought for just a momento as I bring it up on my screen. So beam bending will be on there. So all the stuff that we have been doing on bending, like deflection and slopes and stuff like that, bending stress and shear stress distributions. Those are all fair game topics. And as said, the morning of, I will email you a PDF of the test. You can print it out or otherwise just copy problems down. Do it, then scan it and send it, or take a picture of it or whatever, and send it back to me. We'll do it in kind of this same environment. You'll just be writing things down, and I'll just be here if you need to ask a question. Any questions on that? Any issues with that? Okay, let's get it on then. So today, we're going to be looking at this thing here. So if you want to copy down that problem, that'd behoove you, because I need to move over to the other thing, the document camera eventually, so that we can see what I'm writing. All right, we all good? Silence gives assent. All right, so here we go. So we got this thing. So So the question is, we have this structure, we have some load distribution on it. We have two boundary conditions here, one at A, one at B. It's being held at two points. What's the boundary? How is it being held at A and B though? Is there one pinned, one fixed, both pinned? How is this thing being held?
one is pinned,
Okay.
and then one's fixed.
Okay. So we got a pin joint. We got the other end fixed. What does that mean for the loads at each end?
They're different.
And they are?
One's a force, one's a moment.
Okay. So if we replace those boundaries with forces and moments. So what's the reaction at A? It's this guy here on the left. At a pin joint. Bless you.
Thank you.
And that's an open question for anyone. Nick just happened to be talking. So whoever wants to answer that can.
Just a reaction force straight up on the end of the beam.
Okay. You got it. So we got some reaction force there. Bless you.
Thank you.
And then at B?
And then at B, there'll be 2 reaction forces, one vertical component and horizontal component.
Okay. What you call it? That's true at A too. A pin reacts forces in both directions. Well, what's different about a fixed boundary condition?
It's the force of moment.
Yeah.
Yeah, there's also a reaction moment there too. I'm going to, Danilo, you are right. There are horizontal reaction forces, but because all of the applied loads are vertical, I'm just going to ignore them for right now, because they end up being because they end up being zero. This one is just focus on the other stuff. So we got this. So my next step would be to throw down some positive directions and say, well, some forces, some moments. Yay! So if I say summed moments at B, what would they be?
Reaction at A times L.
Okay, and that would be a positive or negative moment.
Negative.
Cool. What else? Does FB make a moment around B?
No.
No. So no moment from that. Does the distributed load make a moment around B?
Yeah.
Yeah. And how much of a moment does it make?
You need to find centroid.
Right. So you need to find the area of this load distribution. So the height, is W naught. It's L long, and it's a triangle, so it's base times height over 2. Gives us the area of that distribution. So that's like the force from the load distribution. Abbreviating it as LD because I am running out of space. Okay, and then that force is acting at how long of a moment arm?
1/3 from B.
Right. It's with the centroid of a triangle is 1/3 from its longest side, so it's going to be 1/3 L from B. That's creating a positive moment. And then we also have this reaction moment here, which is creating a moment around B by definition. So that guy too, and it's going in the positive direction. 0. Okay, so that's great, but we have 2 unknowns in there, and it gets worse when we try to sum forces in the y direction. Because let me just have FA plus FB minus W naught L over 2. This doesn't really help us at all. We're at 2 equations and 3 unknowns. We cannot solve for all of our loads. So, fear not. That is what we're here for today. So, these expressions are important because they can let us relate loads together, even though we're not going to get a value out here. What we need to do is take these expressions that we have and try to get one more expression to kind of tie everything together and get us a third relationship. And the same as when we looked at statically indeterminate columns and such back in the days of like thermal expansion and all that, when we were messing around in that world back in January and February. We're going to use deformation or deflections as our way of getting our third equation here as well. So let's play the game. We know that in order to get deformations.
Hey, Brother Morris, I have a question real quick.
Yeah, what's up?
Can you click that? Okay, thank you. What's that? That says force from the load, correct?
Force from the load distribution, yep.
Okay. And then wait, what's L over 3? Is that part of the, isn't that the centroid or something like that? Or is that part of that?
Yeah, so WL over 2 is just a force, right? It's not a moment. So we need to express the moment arm, or how far that force is acting from the point that we're summing moments around. So we're summing moments at B, and the centroid of the load distribution is 1/3 the length of the triangle from B, by definition of how the triangle is set up.
Okay.
All right.
Yeah. I just want to make sure, and then that's the bottom. Okay, that's just okay.
Cool.
Thank you, Brother Morris.
Yep. All right. So we know that we have an expression for figuring out deflections of a beam. So, or the deformations of a beam would be a more general way of putting it. So we know that we can get that. What we need in order to do that is, among other things, an expression for the bending moment in the beam. Now, this would be like an internal load. So if I want to solve for that right now, say I'll start at the left-hand side of the beam. I'll draw my free body diagram here. There's my chunk of the load distribution that I'm looking at. Shear force, bending moment. I'll just call it M right now. FA, which we still don't know. So I'm going to be solving for that bending moment in terms of all these other variables. That in and of itself, we've been doing for a few classes now, right? Like we haven't actually thrown numbers at a problem for a while now, at least not in class. So we've done that a few times. So that's not a big deal. We just got to expect it. Numbers are a luxury right now. At present, we're just solving with what information that we have, and the information that we have is that. Yeah. So we can't substitute in for anything yet. We're just trying to come up with another equation here. So So if I do my usual summation of forces or summation of moments thing, so my summation of moments, I got, oh yeah, I got to define my coordinate, sorry, x. There's some positive directions for you. So I know that FA is creating a negative moment around the section. It's x away from it. I got this W prime thing. What the heck is that? We don't want to make up new variables now. But that's kind of like, I've kind of truncated my load distribution. If I take a section like here, the height of my load distribution is down there. It's not W naught. W naught's the maximum of it. It's something else down here. How do I get that? How do I get what the magnitude of load distribution is at my section?
Can you use similar triangles?
You can, as a matter of fact. Yeah, that'd definitely be a way of doing it. Tell what you call. Well, what do you think? What you call? Well, can you describe what you're thinking there?
So I did W O over L equals H over X.
Okay, so
And then I
H is
like
there and your X is over here.
yes.
Okay. So like that.
Yeah, and then I did the cross multiply thing for proportions and then solve for H.
Sweet. Absolutely. So that's a great, quick and easy way of doing it. Awesome. Absolutely awesome. So let me rewrite this on another line so I have a little bit more room. So if I do summation of moments, negative FA X, then an H in this case would be W prime. So now I just need to express W prime as a load. Well, hey, we already did that at least once before in our lives, right? We're just finding the area of this triangle here. So that's just W prime times X over 2, right? Base times height over 2. Except we have an expression for W prime now in terms of things that we quote unquote know. Like we know what W naught is. We know what L is because they're things that define the problem itself. They're not what's called they're applied loads. They're actual physical lengths I can go out and measure with a ruler. Or it's not some reaction force that I can tell you how many sandbags I'm putting on top of something, but I can't tell you how much load a support's taking up, especially in this case where we have to solve for everything because it's all statically indeterminate. Does that make sense? It doesn't say something, but in the interim, that's what I'm kind of saying with this is stuff that we know, even though we don't have numbers for it. It's stuff that defines the problem instead of stuff that's a fallout from the problem. So if I find the height of that, if I find the area of that distribution, be like W prime X over 2 times X over 3. Plus m equals 0. If I substitute in for that, W naught X over L, X over 2, X over 3, plus m equals 0. Cool. And then I can just solve for my bending moment. Get something like this. Is that going to be the, is this going to be the expression for bending moment for the entire beam now?
What is the
Yes.
x over 2?
This guy?
Yeah.
That's from here. I just pulled W prime out. That it's because that's this, right?
Oh, I see.
So that X over 2 just kind of
Okay, yeah.
chilled out for a little bit.
Brother Morris, I don't know if you could. What's the W naught times X over L equals H, which equals W. Why is that? Why is it equal to W?
So if I look over here, this is our similar triangle sort of analogy, right?
Yeah.
For the load distribution. So we said in order to find the height right here, we can do the similar triangles thing and say W naught over L equals H over X.
Yeah.
X is kind of the distance that we're measuring from the end of the beam. So I can solve that down for H, but I didn't call this H, right? I call it W prime.
Yeah.
So W prime. But really they're the same. They're describing the same thing, right? Like H is the height of the load of this triangle here, or the height of the load distribution here. W prime side. Yeah. So they're the same thing.
Okay. I just wanted to make sure.
Yep. Yeah, you can pick whatever variable names you want, as long as you know what they mean.
Okay. And is there a way, like, I don't know if everyone else is like seeing this, but like at least on mine, it's like pretty blurry for some reason. I don't know if anyone else is having that issue, but like, I don't know if you can adjust that real quick.
Yeah, I think it's actually a problem on your end.
Okay.
It must be how it's going. It must be how it's going through the internet, or coming out of the internet on your side.
All right. Well, hopefully it gets better. If I need you to like say something or repeat it, I'll just ask you this.
Yeah. If other folks are having the same problem, we can try switching to something that might be less memory intensive and see what happens. But I don't know how much of a difference changing would make. So unless it's a massively distributed problem, we won't go down that road. And I'll try to write a little bit larger. Okay, so all right, so we got that for our bending moment, right? Does that help at all, Nick?
Yeah, that did help a little bit. Yeah, I mean, I could see it a little bigger, so that's a little better. Yeah.
Okay, cool. We'll just keep going with that then.
Okay, thank you.
Yep. All right, so we got our expression for bending moment on this section here. Can I use that same section to describe stress in the entire beam?
Yes.
Why?
Because there's no like point loads or anything.
Yep. So we made this expression in light of the load distribution that's on top of the beam. That distribution doesn't change. It's the same triangle the full way down, and there are no other loads in the middle of the entire beam. So this bending moment expression is valid for the entire shish kebab. So can go down to my expression for beam bending and just substituted it in there. So that's a 6, not a G. Cool. And where would I get E and I from? I don't know those, right? Where did I get E and I from? What are E and I?
You get them from the material and the cross section.
Yeah, so E is your elastic modulus, which is a material property. So if I know what the material is, I can get that. So that's not really a big deal in the grand scheme of things. I can solve all my equations in terms of E and not have to feel bad about it, because as soon as I know the material, I know what E is. Bam. I, like you said, we get from our cross sections geometry. So that's not that big of a deal either. It's kind of like not having a number to put in for length, because this is something that I can take a ruler out and measure at the end of the day. It's not that big of a deal if I don't know it right now. Oh, it's just like not knowing length. It's fine. So we don't know them per se, but we're just going to keep solving in terms of them. All right. So I'm just going to rewrite these guys up here.
Wait, Brother Mars, what'd you say I was again?
So your second moment of area.
That's right. Thank you.
Or area moment of inertia, or whatever the book likes to call it too. All right, so we got this puppy. Time to integrate. It's such a great day when you can integrate. So y 1 over ei fa x plus b naught x cubed 6l squared. Integrate all of that. Dy 1 over ei is a constant. X squared over 2 minus w naught x to the 4th over 24 L plus C. Sweet. We solve for C right now. Bless you.
Thank you. Thank you.
We solve for C right now.
Yes.
Cool. How?
We know at L, the slope of deflection is 0.
Okay, so we know that by definition of what a fixed boundary condition is, we know over here that dy dx equals 0. For kicks and giggles, we also know that y is also 0 there. And at this pin, you know something about the boundary condition there?
The deflection is 0.
Yep. But we don't know anything about the slope because it's a pin. It's not fixed. So we got 3 boundary conditions that we can mess with here. And well, I just got an equation for slope, so I can at least put in one of them. And it happens, since I'm measuring x from the left-hand side here, that occurs at x equals L. Okay, so dy dx equals 0 at x equals L. So, write that out. So 0 equals 1 over EI. Sorry, I'm getting smaller again. I'll just rewrite it here. Zero equals 1 over EI FA L squared over 2 minus W naught L to the 4th over 24L plus C1. Awesome. All right, so it's pretty straightforward to grab that and solve it all down for C1, right? We can do some simplification on the way. So C1 equals 1 over EI W naught L cubed over 24 minus FA L squared over 2. And if anyone goes, what the crap, where did your negative sign go? I multiplied it through, and that's where these terms are flipped. All right, so there's our constant. So if we write this out again, and let's see if we can simplify it a little bit more so it doesn't take as long to write it. And then we can put that back in. I'm going to have to turn my sheets the other way in a minute. I'm definitely going to have to do that. Hang on. Oh no. All right. So that's our equation for a slope. All right, so now we've got to integrate one more time. I multiply another integral there. So with y equals what? 1 over EI x cubed over 6 minus W naught x fifth over what, 120 L plus, be fancy about this, squared over 2EI W naught L over 12 minus FA times X. That's just another integration, so I need a plus C. You all on board with that? Cool. All right, so how do I solve for C2?
Zero, zero.
Yeah, so if I go back to my free-body diagram, I have three boundary conditions here. Y equals 0 at x equals L, dy dx equals 0 at x equals L, y equals 0 at x equals 0. We already used this guy. And right now we have equation for y for deflection. So I can use either one of these two if I want to. But using the one at x equals 0 would be a heck of a lot easier. So I can, at least for right now, because I can look at this and say, well, if I solve for C2 at my boundary condition of y equals 0 at x equals 0, well, this goes to 0, this goes to 0, all this goes to 0, and C2 is going to obviously equal 0. So that's going to make my life a heck of a lot simpler. So I'm just going to do that. So that's 0. There you go. I've imposed my boundary conditions. All right, so this then is my equation for deflection of this beam at any point x. Awesome. Awesome, awesome, awesome. Now, trick is, what in here did I say that I know? What here did I say I didn't know? Excuse me. What in here do we know? What do we don't? What do we not know? What do we still have to figure out?
FA.
FA is the thing that we don't know, right? We said that E and I, those are straightforward. We know once we know the material or can stick a ruler on it, we know we would try, or stick a ruler on the beam, we can figure those two out. L, stick a ruler on the beam, we can figure that out. W naught, we can count how many sandbags we have piled up on this beam. Okay, set. X is an arbitrary coordinate that we set, so it's not really something that we're really concerned about. What we really don't know goes back to our free body diagram. It's these reaction forces and reaction moment, and the reaction moment. We don't know them. We can't solve for them, and we can't measure them. So those are the things that we don't know. And hey, we got FA in here all by itself. It's the only unknown here in a sense. So long as we know what X and Y are, we can solve for FA. It's the only unknown. Can we specify an X and a Y that'll let us solve for FA? Like, we already used this guy here, right? Y equals 0 at X equals 0. And if we try to put that guy in, all this would go to 0, right?
We could do y equals 0 at x equals L.
Right. Absolutely, because we know that it'll keep our FAs in the equation because the x's won't be 0; they'll be L. Y is 0, but who cares? It's fine. So long as some values there, we can solve for everything else. And that's also conveniently the one boundary condition that we haven't used yet. We've already used y equals 0 at x equals 0. We've already used dy dx is 0 at x equals L. We haven't used this guy yet. So we can throw that puppy in. And say, y equals 0 at x equals L. Yeah. So we do some more algebra with this. We'll cancel those puppies out, make our life just a little bit easier. L cubed, L to the 4th. All right. Now this is a pretty straightforward problem. We just got to group like terms and solve the puppy out, right? So let's see. If I put my FAs together, it's like FA times L cubed over 6 EI minus L cubed over 1/2 is like 3/6. So EI plus, let's see, 24 goes into 125 times. It's like 520ths. Yeah. So W naught 5 W naught L to the 4th for 120 EI minus W naught L to the fourth over 20 EI. My whiteboard's somewhat low tech, so work with me here. So I can solve this guy down and say 0 equals FA times L over 3 EI plus 4 W naught L to the fourth for 120 EI. So that should simplify down to, I think. Mind if I move all this top stuff out of the way? All right, I'll start moving it. So I can keep on going from there. Just solve for FA. Get FA equals 4 W naught L to the fourth. I guess 4 over 120 is like 30, actually. 30 EI times 3 EI over L cubed. Those cancel. That becomes a 10. Gets rid of that. FA, in this case, is that. So, bam! Look at us go. We just figured out what FA is, all in terms of stuff that we kind of know. W naught, again, we said that's how many sandbags are stacked on this thing. We can measure the applied load, and L is the length we can measure. So I go back to my, yep.
Isn't it over 10?
Yes.
Okay.
Thank you. So I can go back to my original summation of forces, summation of moments, substitute in FA, and now all I have left to figure out are my reaction moment and my force at B, which I can now do. So I grab that and say, back in my original free body diagram, summation of forces in the Y equals what? W naught L over 10 plus FB minus W naught L over 2 equals 0. So FB equals what? 4/10 W naught L, or 2/5. 2/5. So that's 1. Or that's number 2, rather, I guess. And I can take that and also look back to my summation of moments. I have negative FAL, or negative W naught L over 10 times L, plus W naught L squared over 6, plus the reaction moment at the wall. Solve for that reaction moment and get something that looks like that one's going to be a little bit more interesting math. 10/60th is 6/60ths, so 4/60ths. Um, $15. Yeah, I can't do the math in my head right now. I think it's a 15th. And there we go. Those are what's called. We've just solved for all of our loads. And the problem is ours. Any questions on this?
You were nice.
Not now, at least.
All right. So again, I'll have your homework back before Wednesday. Hopefully by the end of the day today. But have questions ready for Wednesday. We'll do what we can. If you let me know what your questions are beforehand, maybe we can set up another study session, if you will, at a different time. Because I know that folks have classes right after this. So, all right. That's all I got for today, then.
Thank you.
Welcome. See y'all around.
Have a good day.
You too.
All right.